So this is a quick video of simulating a flow over a 2D cylinder at a velocity of with a free-stream velocity of 100 meters per second. So here's kind of a diagram showing what we have. We have a box and a cylinder somewhere in the middle, placed about eight diameters upstream. Downstream of a boundary condition here. Here we're going to put a symmetry wall and the symmetry wall, and here we're going to prescribe an output. The overall domain is going to be about 32 body lengths. So how do we do this? And we go to star. First thing we do is we go to the geometry. This is one path to do this. There are many paths, but this is one using their basic parts that they have available. Here we can make a block. And the idea of this block is to make a domain that's consistent with what we had looked at previously. So if we look at so what we have is a domain that goes between -8 and 24, -8 and 0 and 8. So you can see and what you see is hold on. So we can't see it right now. What we can do is go to this little thing, which is an object that pulls up, and we can explore some geometry. So here's kind of the geometry that we get. Keep in mind, it should be consistent with, I think this was 32. So we went 8 diameters this way, 8 diameters this way, 8 diameters this way. And we need to go Yep. So it's pretty consistent with it. Okay. So the next thing we need is the cylinder. So here I'm going to add a cylinder. I'm going to add it right at the origin. And it's going to have a diameter of 1. So the radius is 0.5. One thing that's important here is I'm going to try to run this. I'm going to run this in 2 dimensions. So I need to make sure that I can get a plane that falls on z = 0. That's in 2 dimensions. The other thing I'm going to do is I'm going to, what you can kind of think of, at least in this approach, is kind of like a cookie cutter. I'm going to basically put, hold on. I'm going to put it at the origin. So this is the start coordinate. So if you kind of see, you can kind of drag this around and move the cylinder all kinds of different orientations. I don't want that. I want this at the origin. And I'm going to move this off the origin. This is going to be at the origin, and I'm going to move it further than the box. So if we look at you look at the position of the cylinder with respect to the box, it's much larger. And that's because I want to make sure the cookie cutter cuts all of it. If I make this 0 and 1, it should work, but there's a possibility it won't because of errors at the precision of the machine itself. Okay. So I hit create my cylinder. I accidentally created 2, so let me just delete 1. So now we have, so I could, to move this on, I could just grab it, hold the left button, and then drop it and click surface. We could see that we have these 2 different parts. Okay, so how do we get, so what we're really after doing is getting a domain that is consistent with the fluid here. So the fluid is this white region. The boundaries are in this black line, and the other boundary is in this black surface is corresponding to the cylinder. So how do we get that? Go into operations, Boolean operations, and do a subtract. I pick the parts I want to operate between. And then I pick the block. And I hit a CAD and I want to execute it. So what we're doing here is we're obtaining so let's look at this. We have input parts, all the parts you want to input, the target parts, that's the one we want to cut out of, and then the output is the result. So again, from a cookie cutter standpoint, these are all the parts. This is your laid out dough, and any other parts in this, you basically cut away material, and you create a domain that's consistent with the flood. So that's one step. We need to do one more step, and I forgot this. So when we create these basic parts in Star, you basically get these surfaces. So if you go back to parts, you go to surfaces, you get surfaces, and they're all kind of lumped into one. I want to right click on this and split by angle and break them up. The reason I need this is because when we looked at these conditions, we need one boundary condition here, another boundary condition here, another one here, and another one there. So I'm going to go through, and I don't do this all the time, but I'm going to lower wall. I'm going to name things just so it's easy. So this is going to be our inlet, all right? So I right click here, go to rename. Outlet. And then this and this, they're just, I might call them symmetry planes, because that's ultimately what they're going to be in a 2D model. Okay. So once I made those changes, now we have to redo this subtract command, but it automatically updates. So I just hit execute. And I end up with this subtract domain. So let me go back to the scene. So here I go to, or I could go to this geometry scene, and this is basically where we're looking at the geometry. Okay, come back into this. So you can kind of operate between this geometry, this scene here on this tab, or the actual simulation settings here. So when I'm on the scene settings, I could kind of go into the surface, click on this, and unclick everything and focus on this surface of interest. And here's our fluid domain. Okay. So when we come here, we can see we had the outer domain and the cookie cutter cut out. So the next step we want to do is demand that this is a two-dimensional flow. This is very, so how do you do that? You come to operations mesh. You need to badge this for 2D meshing. So what it basically does is identifies regions where you could apply a 2D mesh. So if you look here, it has this red dot. It basically found it. And if you come here, this ends up being our 2D plane that we're going to operate and build a mesh on. Okay. We really only have one more step, and that's to make a mesh. No, two more steps. So the next thing we want to do is actually tell the code where boundary conditions live. So we do this by, I right click here and I assign the part to a region. For this, I always go to a new region for each part, a new part for each surface, a new feature for each curve. And if you do this, what it does is gives you an ability, it doesn't lump everything together. So what I have is a boundary here, 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 and they're all the ones that are consistent with the boundary conditions I need to set. So I come to the inlet and I change it to some sort of an inlet. I'm going to call it a velocity inlet because we're prescribing velocity. For the lower and upper wall, I'm going to call them walls. I'm actually going to call them symmetry planes. And what that is basically gives it a feature that makes it so you have essentially in the potential flow context, no flow through that boundary. Okay, and the outlet, I'm going to call it a pressure outlet. So what we did here is we prescribed all the boundary conditions. Oh, I'm going to keep the cylinder as a wall. You can see it's a wall right here. And then we can start developing a mesh. So I'm going to go to this, what's called an automated mesh in 2D. Select our case. So this only selects surfaces that were badged for 2D meshes. And we can use any of these options. I'll just use the quadrilateral option. Hold on. I'm also going to use a prism layer mesher. And what the prism layer mesher is it puts a lot of mesh in regions where you have boundary layers. And because of that, this is why I called these cases symmetry or not walls. And I'll show you that really quick later. Okay. So here you generate. So once you get to the mesh generation region or point, you have to select a couple of things. One, here's the basic settings for your mesh. Then you move into this mesh base size. This basically gives you a reference size for all the meshing. And if you change it, you can easily change between different mesh resolutions. We'll talk about that here shortly. Okay, so I'm going to say if I have a base size of 1, that basically says my mesh size is roughly the size, this reference size is the size of this cylinder. So for your target size, we also have 100%. So it's basically 100% of this one. So what it's going to try to do is put a mesh size of 1 meter on all these boundaries. We can specify a minimum, 1%. So it gives us a minimum size of this. I'm going to go through and just choose some other parameters. So number of prism layers, how many cells we put in a prism layer. I'll show you that shortly. Let's just go to 2. This is a stretching ratio. I typically like to keep this lower than 1.2. And this is a thickness. So it's going to be the thickness that grows the boundary layers from the walls. So I'm going to make this about, let's just say, I'm going to use absolute, and I'm going to make it about 1/4 of the diameter. Okay, let's just see what our mesh looks like. So, this is our mesh generation button. You can see this all went blank. And what you do here is you come back here and look at the mesh through this button. So this is our computational mesh. You can see on all the boundaries over here, we had about a meter size, and it goes nicely between there all the way to here, and it generates a mesh. So let's just change a few parameters. So first one, let's look at a prism layer. Probably don't know what it is really all that much yet. So I'm going to just focus on that. And I'm going to make this 31 cells in a prism layer. So it's going to make a thickness of about 1/4 of a diameter, and it's going to put 31 cells in between. And you can see that now you can see this prism layer, right? Just right here. And it nicely blends away into the inviscid region. So this kind of a mesh is demanded in the viscous region. The boundary layers not so demanded in the inviscid region away from boundary layers. In general, with CFD, what you need are a lot of cells where you have high gradients. So that's why you need a lot in the boundary layer. You also would typically need them in a stagnation point and wakes. Okay, so let's look at one more thing. This is surface curvature. So basically, as we have it now, we have 36 cells per circle. So it has about 36 points around it. We can increase this And we should see more points around the radius to give us a better mesh. And a mesh where in more cells where you have more curvature. This is a simple case with a cylinder. You get a vision with, if you have an airfoil, it gets, the story gets to be a little more complicated. So for example, if you have an airfoil right here, it might try to put 100 and, well, I don't know, maybe like 63 points on this region. And it goes down here and it adds more here. Okay. So now that we have all of these cases run, or we have a mesh, we have, now that we have the mesh, what we need to do is set up the model. So here we go to continua. Continua basically tells us where to set up the model. So I'm going to go to right click on physics. And I'm going to choose some of the model settings. So I'm going to go to steady. I'm going to go to a gas. I'm going to go to a segregated flow solution. These are just conventional methods. There's a lot of options, and it goes much deeper than here. Constant density. I'm going to use turbulent and a Spilart Alamara's turbulence model. And in this settings, we basically chose all the physical stuff we might need to use. Again, I want to emphasize there are a ton more we can use. But this is a starting point. Okay. So once we do that, the next thing we need to do is set our boundary conditions. So here, oh wait, I want to show you one more thing with the mesh. So if I decided to switch these to a wall, and then I generate the mesh, it should generate prism layers here and here, which is consistent with if you wanted to model this in a wind tunnel, you might have these, but it takes a lot of effort to model these small boundary layers. And because of that, I almost always, and the boundary layers aren't that important for the most part. So because of that, I typically just use a symmetry plane, and it looks like an Inviscid wall, and you get away with the blockage effects in the wind tunnel, but you don't have to worry about boundary layers in the wind tunnel. Okay. So we need to go to boundary conditions and set the inlet. So I recall our inlet velocity is 100 meters per second. So I come here. So once you set your inlet, you can kind of dig into different options. Here it's boundary normal. It says that flow always comes in the boundary normal direction. It's consistent with what we're after. And then we go to set the velocity. We change it from 1 to 100. These are basically no flux through the boundary conditions. And then we basically set a pressure. So I'm just going to use 0 pressure. It's a gauge pressure. So it's basically going to specify 0 pressure here, propagate pressure upstream. And it's going to specify 100 meters per second velocity here. And velocity propagates downstream. I'm going to do one more thing, and that corresponds to probing. Here, I'm going to make a new report. One report we probably want to make is something either like a force coefficient or a force. I'm going to do a force coefficient. So basically, if I do this, I can make a drag coefficient. I'll call it CD. I put the direction in the direction I want the force coefficient, so the X direction. I have a reference density. So if I come over here to gas, I can look at the density, which is 1.18. So I come back to the report. I have a reference velocity, you set it to 100. And a reference area, you always remember you need an area for this. This is that area, which is 1. And then we have to do one more thing, and that's select the surface that you're going to compute it on. So in this, it's all in the regions. These are the parts. They convert into these regions, and we want to select the cylinder. So with that in mind, the last thing we could do is say how far we want to run it. We'll run it for 1,000 iterations and just see what we get. So when I'm ready to run, I'm going to hit this running person. What we see here are residuals as a function of iteration. That basically is a measure of how accurate the governing equations are. So here we're solving the Reynolds average, Navier-Stokes equations. It's a, and you can see it's converging to a final result. The other thing we can do is select this, right click on this, and create a monitor and plot from report. The reason I like doing this is it tracks the drag coefficient as a function of time. So we hit 1,000 iterations, it stopped. What I'm going to do is go to look at a scene, go to a scalar scene. And it defaults to show the entire region in here. For a 2D, it makes sense. I'm going to right click on this, and I'm going to find velocity, go to magnitude, and we can see the velocity magnitude we get in a domain. You can see a little bit of like jaggedness. So if I click this, it's the mesh. You can see it's plotting a single value for every cell. If I go back to here to the scene plot, go to scalar and change from automatic to smooth field, it gets to be nice and smooth. It does some averaging, and it starts looking like a reasonable result. So I'm going to clear the solution and just show you this. So when you're done with your solution, you get a solution, clear. Now you start from square one. I'm going to rerun it and show you. You could see how the model is evolving. You can see some of the unsteady characteristics in the solution. Recall we used a steady model, which is very invalid for an unsteady flow. And you could see it converging. I'm going to go here and show you, this is the predicted drag coefficient, and you can see it's converging to what appears to be a final result. You can see, again, the residuals converging. And you can see that at some point it gets to be a nice and stationary result. And you have to get to some point where you're happy to say it's good. So if we look at this, we have a nice result. If you come here, go to edit, copy. So pasting my results. Oops, hold on. I right click on this white part, hard copy to clipboard, paste the results in here. Same for this. You know, if you have this kind of a plot, make sure you go to scene plot and make some of the legends legible. It defaults to pretty small values. So I prefer, you never want to have a plot that you can't really read stuff. So you could come here, right, click on this thing, make it something that you can actually read, right? Click here. And then you might also do it with the labels too. And I right click here, hard copy the clipboard, and you're able to get an understanding of your results. And it should not take all that long. Okay, so that's it for this 2D tutorial. Again, key steps are creating your parts. This part was a outer boundary. This part represented the solid surfaces. We did this to cut things out. We we made sure to break up the outer boundary into boundary condition or the different surfaces so we could apply boundary conditions. Once we had this part, we made it 2D, we made a 2D mesh, we set up, we converted this into a region with boundaries consistent with the physical character. We remeshed the case, then we developed representation of the physical character. We made a report and a flow visualization option so we could look and see what's going on. This report, we right-clicked here and created a monitor and plot that gave us this. Monitor is a listing of the report as a function of iteration. And that basically summarizes, the basic steps. I will say that if you get to this kind of a steady model and it doesn't look good, the typical path you do is you migrate from steady to unsteady. You need to change a few settings here, specifically in implicit unsteady. You have a time step size, always run things higher order, so second order. My approach to identifying a time step size, I just default to 0.01. My approach to this is you find, okay, how long will it take a fluid particle moving out here to reach the trailing edge? This is called a convective time, which is the length over the infinity, right? So that's so it's how long does it take to move L when you're moving at V infinity? So in this case, it is roughly, so this case is 1 meter divided by 100 meters per second. So that is 0.01 seconds. And we typically divide that by 20. And you want at least 20 time steps over there. So we end up with a estimated time step of about 0.005. So I'm going to use that here, 0.005. Oops, I missed a 0. I'm going to just mention one more thing. Once you move into this unsteady mode, I like to make a new monitor and plot. And the reason I do that is because the previous one is set up for steady food. So this is as a function of iteration. This will be as a function of time. The other thing is, whenever you run an unsteady flow, you almost always want to converge it with a steady result first. Okay, last comment on a steady flow. We need to specify a certain number of time to run it, inner iterations. So this is a nonlinear iterations. I usually like at least 10. You want a physical time, it depends on your convective time. I think we said it was about 0.01 seconds. So if we run it for 1 second, that's going to be 100 passages. That's a little bit too much. We could probably get away with 20% of that. So what we can do is, one more thing. When we go into the scene scale, come here, go to this update thing. And what this does is updates how many times you see an update here. It defaults to every iteration. If you're running it time accurately, you really want to only update it every time step. So if I come here, we can see an update every time step. If you come here, we can see the drag coefficient each time step. We can see here it continues at each iteration, but we iterate 10 times each time step to obtain the results to net or soak. So you really want this value. You can see this, you can see this. One thing you'll see are residuals. And you see when you go from steady, it's just converging down. Then you go to unsteady. So I click this thing and I can kind of zoom in and see what they look like. What this is every new time step you start here and you converge every 10 iterations to a new value. And you can see you get to a much lower residual. It's because it's more consistent with the unsteady framework. So again, each one of these saw-like values is a new time step. And you start off not converged and you converge with more and more iterations. So if I show you this, we could set this to, I don't know, 300. What you see is we obtain, when you see this jaggedness, that's machine zero iteration. You don't want to run it forever. So you want to do is tune this to some value right near this kind of point. So maybe it's 25. And you can see most of the equations seem to converge quite well. But for the sake of time, I'm going to go to 5 and just show you what kind of the result looks like comparative. So you can see the drag coefficient is converging to a roughly constant value. Same for here. And our residuals seem to have changed, but seems to be working pretty well. So that's a rundown of a 2D case. Let me just, okay, so now we've run the entire timeline. And you basically have the result. I'm just going to show one more thing. And if you want to run an Inviscid case, I'm actually going to go back to steady flow. So I'm going to pull in the unsteady off, go back to steady. I'm going to go back here and I'm going to get rid of, so you can start getting rid of things. So now you can either start from scratch or you could start getting rid of things. And you can select this Inviscid option. This is consistent with the potential flow. So here I'm going to just hit clear solution, clear everything, rerun this case, and we should end up with a potential flow solution. So note that now this case isn't showing up every iteration. If you want it to show up, that's because I had said update every time step. Here we have to update every iteration, and we can see we can get back to what we had before. So things are kind of moving around a little bit because it can be a little bit hairy numerically, but it seems to be converging reasonably fast. We converge to roughly 0 drag, which is consistent. And we get residuals that are basically mostly converged. So that's all I wanted to show you for this. Please, I hope this helps.